Uh, Student friends, now we'll discuss the important article in the chapter as Ewald's construction and Bragg's law in reciprocal lattice. In my earlier lecture, we have discussed the Bragg's law in direct lattice, and we have obtained Bragg's condition for reflection or diffraction of X-rays from crystal planes, and that condition we have obtained is it is 2d sine theta is equal to n lambda. That condition we have derived. The condition is 2d sine theta is equal to n lambda. In that condition, we can write as 2d sine theta is equal to n lambda. So d is the interplanar spacing corresponding to the crystal planes. Theta is the glancing angle made by the incident X-rays with crystal plane, and n is the order of reflection, and lambda is the wavelength of monochromatic X-rays which are incident on the crystal planes. Now we'll obtain the same Bragg's law in reciprocal lattice by Ewald construction. So actually we have to obtain the Bragg's law in the reciprocal lattice, and that can be done by making use of the Ewald's construction. So in order to study this Ewald construction or Ewald sphere, let us consider the regular and periodic arrangement of the reciprocal lattice points. Means we have to consider these are the regular and periodic arrangement of reciprocal lattice points. So we have studied how to construct the reciprocal lattice vector in previous lectures. So I will again repeat, each reciprocal lattice is at a distance of reciprocal of interplanar spacing corresponding to that planes from a common origin, and its length is equal to reciprocal of the interplanar spacing, and it is normal to the crystal planes. So that we have discussed, and how the reciprocal lattice vector is represented, that also we have discussed in earlier lectures. So let us consider this is a periodic arrangement of the reciprocal lattice points. Obviously, it is a two-dimensional reciprocal lattice that we have taken, and each point has a specific set of parallel planes, and it has Miller indices and interplanar spacing. Now, in order to construct the Ewald sphere, or in order to study or understood the Ewald construction, let us consider any point A, any arbitrary point A. It may not be a reciprocal lattice point. It can be any point. So you can consider, so this should not be A at this point. So it should be anywhere. It is not necessarily the reciprocal lattice point. So from this point A, let us consider a vector AO of magnitude 1 upon lambda. So consider a vector AO and its magnitude, it is a vector, and its magnitude is 1 upon lambda. So this is a vector. Now construct the sphere of radius 1 upon lambda in this given arrangement of the reciprocal lattice point, so that certain number of reciprocal lattice points will lie on the surface of that sphere. So let us consider this is the sphere, and suppose these are the reciprocal lattice points. So this reciprocal lattice point lies on the surface of the sphere. You can have this reciprocal lattice point which lies on the surface of the sphere. So certain number of reciprocal lattice points, they lies on the surface of the sphere. So in this way we have to draw the sphere. Now let us consider this point as a reciprocal lattice point here, and suppose obviously this reciprocal lattice point is nothing but a set of parallel planes. So suppose these are the parallel planes, and these parallel planes belongs to that particular reciprocal lattice point. So Let us assume that H dash, K dash, L dash are the Miller indices of this reciprocal lattice point. Then how will you construct the reciprocal lattice point? So construct the reciprocal lattice point. So here we have to again make one assumption is that the end point of this vector AO must be a reciprocal lattice point. That is another condition. So A point, this point A is not, it may not be necessarily at the reciprocal lattice point, but this it should terminate at the reciprocal lattice point. Vector AO should terminate at the reciprocal lattice point, and its magnitude is 1 upon lambda, and construct the sphere of radius 1 upon lambda so that it will intercept certain points in this arrangement. That means certain reciprocal lattice points will lie on the surface of this sphere. Now we have considered this set of parallel planes having Miller indices H dash, K dash, and L dash. Now, that means if this is the point B, we can construct the reciprocal lattice point. So suppose this is the interplanar spacing corresponding to this set of parallel planes, and suppose it is D, H dash, K dash, L dash, and we can construct the reciprocal lattice vector by drawing the normal to these planes. This OB is normal to these planes. And it is what distance? It is at a distance which is proportional to the reciprocal of the interplanar spacing. So that we are that is how reciprocal lattice point can be obtained, and or it can be constructed. So I think you might be getting my point that these are the planes corresponding to which we have constructed this reciprocal lattice vector OB, and this reciprocal lattice point is at this point B. Now it is obvious that if you join this AB, vector AB, so again it will be equal to 1 upon lambda, because this O will be the, remember this O is origin of reciprocal lattice point. This O is origin of reciprocal lattice. So O is origin of reciprocal lattice, and this A is center of the sphere. It is the center of the sphere. So obviously this AB will have magnitude 1 upon lambda. So in this way we can consider or we can consider the geometric construction of this sphere, and what is the vector OB, what is the vector AB, all these things that you can write. So this is the vector AB. Now let us assume that the coordinates of this point B, they are H dash, K dash, L dash. That means while constructing the reciprocal lattice, we have seen that suppose this is the origin, and suppose this is the 1 0 0 plane. Then you can construct the reciprocal lattice by drawing the perpendicular distance, and which is at a distance, we can call this point as OR, and that is nothing but 1 upon D100. However, you can consider a plane having Miller indices 200, and reciprocal lattice point corresponding to this plane 200 can also be in the same direction, and suppose it is S, and it will be at a distance of 2 by 100. So we have seen construction of the reciprocal lattice point. In this way, let us assume that this point B has coordinates, and these coordinates are nothing but H dash, K dash, and L dash, which may have the highest common factor n. So these reciprocal lattice, these Miller indices may have the highest common factor n. That means we can say that the coordinates of this point B are nothing but nh, nk, and nl. So from this you might be able to understand this concept. So the coordinates of this point B, they are nothing but nh, nk, and l, where n is the common factor, highest common factor that we can call it as, and HKL, they will not have a common factor. If it has a common factor, it will be only unity. And obviously the vector OB is the reciprocal lattice vector. So this OB is nothing but the reciprocal lattice vector, and therefore it must be normal to these planes. So it is normal to these planes which are shown here, and therefore we can write the magnitude of length of vector OB as, therefore what we write, we'll write the magnitude, we can write the magnitude of vector OB, and that magnitude of vector OB will obviously equal to it is equal to either 1 upon d h dash k dash l dash, or it is proportional to or it is equal to n divided by d h k l. So like that. So from this concept you can write this as the magnitude of reciprocal lattice vector is nothing but n divided by this d h k l. So HKL, it has not common factor, and n is the common factor corresponding to the Miller indices at the point B, which are h dash k dash l dash. So that is the magnitude of vector this n. Now again here from this geometry you can draw a normal to OB, so that these angles are angles EAO. This angle is theta, or this angle EAB, this angle is theta. So we can draw this normal. So this normal AE, it bisects the angle at A, and suppose this angle EAO is equal to angle EAB is equal to theta. And from the triangle AOB, or we can write this as from triangle AOB, we can write this OB is equal to, we can write OB. So it will be bisect this vector OB, so it will be twice OE, it will be twice O into E, and this is nothing but twice. So this is right angle triangle AEO. So right angle is here, and this will be the hypotenuse, and therefore OE will equal to 1 upon lambda into sine theta. So OE is nothing but 1 upon lambda into this sine theta. So that we can write again OB is equal to, this is nothing but 2 divided by lambda into this sine theta. So we have also calculated the magnitude of vector OB by considering this AE vector, and obviously AE is parallel to the crystal plane. Remember, this AE is parallel to the crystal planes since AE is perpendicular to OB. So we have calculated OB in two ways. We can equate these two. We can equate this OB and we can equate this OB, so that we will get n divided by, so that you will get n divided by DHKL is equal to 2 divided by lambda into this sine theta. Or we can write this as 2d sine theta is equal to n lambda. So here d is HKL. So in this way, you can obtain the Bragg's condition, and this condition is same as that of the Bragg's condition that we have obtained for direct lattice. So this is the Bragg's condition in reciprocal lattice. We have considered here the construction of the reciprocal lattice. That means it is observed that if the coordinates of the reciprocal lattice point, which are nh, h dash, k dash, l dash, that means nh, nk, nl, contain a common factor n, then it represents the nth order reflection. So this is a common factor. So it will represent the nth order reflection, nth order reflection of the X-rays from the crystal planes. So again, one thing is to be remembered is that in order to have the Bragg reflection, what is the condition? Condition is that the end point of vector OA must be a reciprocal lattice point, and the OB vector OB it must terminate at the reciprocal lattice point. Means the point B must lie on the surface of the sphere. So that is the condition. Then and then only you will observe, or you will get this condition. Otherwise, you will not get condition. So to satisfy Bragg's condition in reciprocal lattice, the reciprocal lattice vector must terminate at the reciprocal lattice point. Means the reciprocal lattice point must lie on that particular sphere, and then only you will observe the Bragg's reflection. So this sphere which we have drawn, which intercepts the reciprocal lattice point and which shows the Bragg reflection, this sphere is called as Ewald sphere, and this total arrangement is called as the Ewald's construction. So that is how one can understood what is the Ewald's construction and what is the Ewald sphere. Now we can obtain the reciprocal lattice point in another form also. For that, what we'll do, we'll consider the this is the Ewald sphere, and now we will consider the same situation, but now we'll consider the center of the sphere as A dash, and it represents the vector A dash O dash, but we have multiplied by this 1 upon lambda by a constant factor 2 pi. So instead of taking 1 upon lambda, we'll represent this as 2 pi by lambda, and let us 2 pi by lambda is nothing but the propagation wave vector, and it is a k. So vector k is equal to 2 pi by lambda. That is, we have consider by multiplying 1 upon lambda by common factor 2 pi, and obviously this reciprocal lattice point will be at this b dash, and this will be reciprocal lattice vector. We know that how it is represented. It is represented as HA star plus K B star plus LC star, that we have discussed, and this A dash B dash is nothing but a vector which will be in same magnitude as that of the A dash O dash. Now we can find out represent a vector k by a vector A dash O dash, and vector O dash B dash is the reciprocal lattice vector, and it is given by G, just I have told you. And from geometry or from this triangle law of vectors, we can write this as vector A dash O dash plus vector O dash B dash is equal to vector this A dash B dash. So we can write from this triangle law of vectors as this vector A dash vector B dash is equal to vector A dash O dash plus vector O dash B dash, or we can write this is nothing but k, we have assumed that, and this is nothing but the G. So these are the vectors k and vectors G. But what is the condition? Condition is that for Bragg reflection to occur, this point B dash must be on the sphere. That means again we can write here as this vector A dash B dash is equal to vector A dash O dash. So then and then only you will observe the Bragg's diffraction. So point B dash must lie on the surface of this Ewald sphere, and therefore we can write this as we have A dash B dash is equal to this k plus G. So we can write this as k plus G square is equal to A dash O dash is nothing but it is a k. So again it is a k square, or if I expand this, I can write this as k square plus twice kg plus this g square is equal to k square, or we can write this as k square will cancel. So this twice kg, this is a wave vector, this is a reciprocal lattice vector, plus this g square is equal to 0. So again, this is a Bragg's condition. You can write in this vector form. So this is the Bragg's condition in vector form, and it is very useful in order to understand the concept of brilliant zones. The concept of the brilliant zones can be understood easily with the help of this vector. Again, we can write dash. Again, we can write as we know that this vector a dash o dash is equal to vector a dash b dash, means we can write this as k square is equal to k dash square, or we can write this as or we can write this as k is equal to, this is k dash, but this k dash is nothing but k plus g just a minute. So this is nothing but, so this can write as k dash is equal to k plus g, and from this equation we know that k dash is equal to k, and therefore I will write this as k dash minus k is equal to, this is nothing but delta k is equal to g. So this is also a Bragg's condition. We can write this in another form. So k dash minus k is equal to delta k is equal to g. This also indicates that scattering does not change the magnitude of a vector k, but its only direction is changed, and the scattered wave different from the incident wave by the reciprocal lattice vector. So in this way, we can understood this construction of the Ewald sphere or Ewald's construction, and how to obtain the Bragg's law in this reciprocal lattice. So one more thing that I would like to again explain is that this vector a dash o dash is in the direction of incident X-ray. So it represents the incident direction of the X-rays, and this a dash b dash, it represents the direction of reflected X-rays. It represents the direction of reflected X-rays, and we have drawn a plane which is parallel to the plane side B, or like this. This is the AE, and this is the reflecting plane. We have considered this angle as theta. So this angle is theta. So this is the reflecting plane. This is a reflecting plane. So angle made by the incident X-rays with respect to plane is theta, and hence this theta is called as the glancing angle. It is called as glancing angle. So in this way, you can also represent in which direction the incident X-rays will be, in which direction reflected rays, what is the, where is the reflection plane, all these things that we can understood from this Ewald construction, and we can derive a Bragg's condition in a reciprocal lattice. So hope you might have enjoyed this lecture. If you have liked this lecture, please share my YouTube channel so that I can prepare more and more lectures and share for you. Thank you for watching this lecture.